Hello, this is FlippedHarber for Precalculus. In this video we'll be covering section 4.3, Logarithmic Functions. The objectives for this lesson are to change exponential expressions into logarithmic expressions, and to change logarithmic expressions into exponential expressions, evaluate logarithmic functions, determine the domain of a logarithmic function, and graph the logarithmic functions. The outline for this video will start by talking about what a logarithmic function is in a generic base A. We'll talk about the domain and range of logarithmic functions, graphs of logarithmic functions, the natural logarithm. We'll talk about graphing logarithmic functions with transformations, and then we'll take a look at some examples. So I know logarithms seem to cause a lot of people some problem. And the way I think about it is a logarithm is like an inside-out exponential expression. So when we say that y equals the log base a of x, that's equivalent to saying that x is equal to a to the y power. So that's why I say that it's an inside out. That a that's on the logarithm becomes the base number with the exponent. Now a has to be greater than 0. You can't take a logarithm with a base that's negative, and a does not ever equal 1. A log base 1 is basically useless. Now, the way that I think about it, when I see a logarithm, especially a log base a as we see here, what I think in my head is, what power do I need to put on a to get x? So if we see a log base 10, which is a very common logarithm just because we work in base 10, I'm always asking myself, what number needs to go on 10 to get this number that the logarithm is working on? So really, a logarithm is a way to solve for a power, and that's really the reason that it was invented. It was actually invented by a guy that was studying elliptical orbits, and he needed some way of dealing with some exponents. So he developed the logarithm to solve for those exponents. Now, the domain and range of a logarithmic function, let's start by pointing out a simple fact that logarithmic functions are the inverses of exponential functions. So we just did a section on inverses, and we know that the domain of one function is equal to the range of its inverse. So the domain of a logarithmic function is equal to the range of an exponential, and vice versa. The range of a logarithmic is equal to the domain of the exponential. So whatever numbers we can plug into one, that's what we're going to get out of the other. Now, quite simply, our domain for a basic logarithm is any positive number. We can't take the logarithm of 0. We can't take the logarithm of any negative numbers. So our domain is all of the positive numbers. Our range is any real number. We can get out positive numbers from logarithms. We can get out negative numbers. We can even get out a 0 from a logarithm. So our domain is all positive numbers, and our range is all real numbers. Now, taking a look at a generic graph for a logarithm, this would really represent any logarithm base a. They always have a domain that's the positive numbers. They always have a range that's all real numbers. We have a vertical asymptote at x equals 0, the y-axis, and we have an x-intercept of 1. Now again, this is for any log base a, as long as a is greater than 1. A logarithm where a is a fraction or a decimal is going to look actually quite a bit different. I'll leave that to you to figure out on your graphing calculators. So remember that when you're graphing these things, you've got a vertical asymptote at 0, and it should be going through the x-intercept at 1. Now obviously there's ways of changing this. We can apply all of our transformations that we've dealt with before. We can do shifts or translations, we can do reflections, and all that good stuff. Now here we see a comparison between a generic logarithm and its inverse, the exponential function. So you can see that they are reflections over that diagonal line. Again, that line is y equals x. So this is just showing that yes, they are inverses because their graphs are reflections over the y equals x line. Now, there are some special logarithms. Basically, there's two special logarithms. One is kind of generically special because we work in base 10. It was decided that a log base 10 is somewhat special, but that's really just because we have 10 fingers. If human beings had been born with 12 fingers, we'd use log base 12 as being special. But there's a thing called a natural log where this truly is special. This is based on that number e that always just shows its ugly face, and we decided to name it, feed it, keep it, make it our own. And it's really quite useful with logarithms. So we give it a special name. We call it the natural logarithm. And the natural logarithm is really just the log base e. It just happens so often you might as well give it a name, pet it, and call it your own. So when you see ln, that's actually read natural log. It's from the, I think, French version of it, or maybe the Latin version of it, that it's ln, but it's just the log base e. Now again, here's a couple graphs. The graph of the natural log is the inverse of the exponential e to the x. Again, the curves are reflections over the line y equals x, as we would expect any inverses to behave like that. So we still have that vertical asymptote at 0. We still have that y-intercept at 1. Alright, now let's talk about graphing logarithms. Here we see the graph for our natural logarithm, and we want to do a couple transformations to this. We want to change it into g of x equals negative natural log of x minus 1. Now obviously what we're going to do is apply the transformations that each of these changes should cause to our graph. So the negative in front of the logarithm shouldn't be a big surprise that it flips it over the x-axis. Whenever you put a negative in front of the function, it's going to flip it over the x-axis. This does not change the vertical asymptote. We still have an asymptote at 0. It's just that the curve is going to be pointing up instead of down. And it does not change our x-intercept. Our x-intercept is still 1, but instead of going through 1, going from below the line to above, it's going to be above and go through and be below. Now the minus 1 inside, that's an inside change, so you got to think, oh yeah, that's right, inside changes, it behaves opposite what we expect. So that minus 1 is going to move the graph right 1. Now along with the curve, obviously it's going to move the x-intercept, but it also moves that asymptote. So the asymptote moves over 1 as well. So when we make those two transformations, this is what our graph ends up looking like. You can see that it's been flipped over the x-axis. It has been moved right 1. The asymptote is now at x equals 1. Our x-intercept is now at 2. Okay, so let's look at some basic examples to try to wrap our heads around this whole logarithmic expression and what logarithms do for us. So what we want to do here is change these two logarithmic expressions into equivalent expressions using an exponent. First one shouldn't be too difficult. I need to come up with an exponential equation that works out with the three numbers 4, 16, and 2. The other one might be a little difficult because we've got a variable in there, but we just follow the pattern. So looking at the first one, well, 4 squared equals 16. So that's my expression. It's now an exponential expression instead of a logarithmic. And it's pretty easy to put it together because this is the only way that we can arrange them to get an exponent that makes it a true statement. So if I basically follow this pattern, my 2, which is my log base in the second expression, becomes my base number. The x from the right side of the equation becomes my power, and it should equal 6. So the equivalent expression is 2 to the xth power. I know that sounds weird, but 2 to the xth power equals 6. Alright, let's take a look at some other examples where we need to find the exact value of these logarithms without using a calculator. Now, you should have learned about logarithms before. You might know how to put weird base logarithms in your calculator. The idea is that you should be able to figure these out based on your understanding of logarithms. So when I see these logarithms, here's what I think. Log base 8 of 8 is asking me what power do I put on 8 to get 8? Well, that one's pretty obvious, I think. It's 1. 8 to the first power equals 8. So that's actually a property of logarithms. If your base number and the number that you're operating on are the same, then it equals 1. What about this second one? What power would I put on 3 to get a fraction 1/9? Well, if I square 3, I get 9. How do I make it a fraction, though? Well, a negative exponent would make it a fraction, so my answer to this one is -2. Okay, well, what about this bottom one? We can totally do this. A log base 1/3 makes sense. We can't use negative numbers for the log base. We can't use 1. We can use decimals. We can use fractions. So what power do I have to put on 1/3 to make 9? Well, you got to stop and think. I got to flip it. I got to change it from a fraction 1/3 into a whole number. So again, I'm going to use a negative power to do that. And then how do I change a 3 into a 9? Well, actually, I get the exact same answer for this one. The log base 1/3 of 9 is equal to 2, because that's the power that I need to put on 1/3 to flip it over and turn it into a 9. Okay, so that's it for this section. You should be fairly familiar with logarithms. It's time to start the homework. I'll see you in class, and I'll see you online.